Hello, I would like to explain how I wrote the code for ALUdecoder. So first, I looked at the table of values and used that to write some Boolean expressions for each of the 3 bits of the output ALU control. From those Boolean expressions, I worked backwards to draw out these gates in a program called Logisim to test whether they worked. And Logisim lets you kind of poke the Boolean inputs like this. And through toggling these different bits, you can see how the output is changed. So this allowed me to quickly test that my Boolean expression was correct before moving onto the next step, which was writing it up in system Verilog. So first I started with the function signature, and I commented out in the Boolean expression, just so it was easy to reference while I was writing this up. Then, much like how I drew out the diagram of the gates, I worked backwards from the end. I literally wrote the code starting from the last line, and then working backwards through the gates in order to build this circuit up gate by gate. As a rough heuristic to tell whether my code is correct, for every logical operator in the Boolean expression, I should see roughly 1 line of code which corresponds to that operator. And that's exactly what I got. After that, I moved on to testing this. I first tried to write my own test bench, but I had some errors because I forgot to set the bit widths for this, and I forgot to set the bit width here. But after fixing those, my test bench was able to pass all the cases. I'm not going to run this now because it would take too long. And for reference, the test vector file that I used was just copying down the values in the original table we were given with this order of operands. All other combinations of inputs can be treated as don't cares because ALU control only needs to output a signal for these combinations of inputs.
And here's my programmed FPGA. So the switches at the bottom are set up exactly in the same order as the arguments in the Verilog file. So here's op5, func3 from smallest bit to largest bit. This one is func7, and this one is ALU op. So for convenience, I've copied the table of outputs down here, roughly. And I'm just going to go through row by row and show that the output is as expected. First of all, with everything off, ALU control should be 0. And as you can see, no LEDs are lit up here. For the second row, when ALU op is 1, 0, reading from the smallest, when this is on, the last LED should light up, and it does. For the next rows onward, ALU op is going to be 0, 1, so I'm just going to toggle this now. Right now, in the third row, everything is off, everything else is off, so this is correct. Moving on to the row where func7 and op code are both 1, we should see ALU output has the last LED on. So we turn on both opcode and func7, and the last LED turns on. For the next row, we have func3 is 0, 1, 0, and everything else is don't cares. So let's flip the middle bit of func3, and as we can see, the ALU control turns to 1, 0, 1. For the next row, func3 becomes 0, 1, 1, reading from the smallest. So we toggle this on, and the output switches to 0, 1, 1. For the next row, func3 is 1, 1, 1, so I'm going to flip the last bit of this on, and the output should be 0, 1, 0. And then for the last row, we're showing that no matter what func7 and opcode are, as long as they're not both 1s, ALU control will remain 0. So we can see here just flip func3 off again. And with opcode and func7 both off, it's off. With just one of them on, it's still off. But with both of them on, the output becomes 1, 0, 0.